these values in a thermal analysis. I think, honestly, it should be explained to the customer at every simulation that there is a kind of problem, and always it's always possible because we use many Chinese, kind of components, and values are fabricated anyway. But if we are talking about FPGAs or processors, then getting an analysis model is a must.
Omer, sorry, I'm stopping you, but you can mute the participants. And it will
I don't want to mute the participants.
No, because they are making noise. That are making noise
so
making it hard to hear you.
Yeah, I know. So participants, I'm intentionally not unmuting everybody because I wanted to be interactive. We're going to get rough stuff here. So I'm not going to mute all of you, but don't talk if it's not a question. I mean, watch the webinar, ask a question if you want. Just interrupt me. Feel free to interrupt me, but don't talk with each other unless you want to mute yourself. Okay? Yeah. We're set now, right? Okay. Package thermal resistance is commonly in use. Junction to ambient. The junction to ambient is a characteristics that you get in data sheets. It's called theta or RJA. It means the thermal resistance from the junction, from the silicon of the chip to the ambient, which is, again, we said the word. It doesn't make sense to use this particular characteristic because it's dependable upon the configuration we have. Of course, if we decide to put non-conductive material above the chip and not allow the heat to flow at all, the chip will heat up and explode. Then again, we'll cool it with a fan. So what does it mean? We'll see later. The internal thermal resistance, the RJC, is the thermal pass from the top layer, which means that in this model, the top layer is considered to be isothermal. Okay, so you don't solve problems like this with natural convection or anything like that. You could, but you're more restrictive and you're more conservative when you solve kind of problems with pure conduction. So if you pass with pure conduction, then certainly you would pass it with natural convection. So that's the thermal resistance from the junction to the top. And there's a thermal resistance from the junction to the board. Everything you see here is standardized. It means every one of them has a particular JEDEC experiment, which we'll see right now. The theta junction ambient, the thermal resistance from junction to ambient with no forced convection is done on this exact setup. And everything is known in the setup. You know, there are 4 layers here. It's written in JEDEC. No, I didn't write it, but it doesn't matter. JEDEC 5.1.3. And this one is for force convection. And then you have all the conditions are given. That's how the vendor is supposed to get these values to you. So I mean, this value you can characterize a component with this value, but it doesn't mean a lot. It can help you derive a theta JB that we'll see afterwards. Here you see the test done for achieving theta JB, thermal resistance from the junction to the board. Being properly set up, the board is here, water channel here, everything is written. There's a standard which explains exactly which power we use, which cooling we use, how much force is applied on the chip, what the installation means, and when and where we place the thermometer to check the temperature, like 5 millimeters minimum, or it's exactly 1 millimeter, usually from the chip itself, the temperature of the board. So there's no, these are boundary condition dependent, and they are defined completely in the JADEC. Okay, what you can use is do theta J. Yes. I can't understand you, and you're possibly not talking to me.
Yeah. Tom, can you unmute all the persons, because there is some noise from the participant. You can mute all the participants.
Yeah. I mean, I would like not to do that. I mean, there's not a lot of noise from the participants, and I am asking again because I really want it to be interactive. If I mute everybody, then you'll be muted for all you'll have to send me a message, and I won't see. Just be quiet. I mean, you're adults, you can be quiet. What you see here is utilizing simulation. This one is done with IcePack, utilizing the same simulation we did here. Okay, for theta J, we have a theta JA, and we want to extract exactly according to the JEDEC placement, the theta JB. So we can have an iterative process, the simulation, to if we don't have a theta JB, which is a kind of data which is a must-have in a simulation, even though I told you we're not allowed to use it. So here you see utilization of simulation to derive from theta JA, a theta JB. There is JEDEC introduces a quantity known as the phi JT, phi TA. It's called the characterization parameter. Do not use this in simulation. Okay, this is not for simulation. This characterization parameter means what happens when all the power goes to the top, or what happens when all the power goes to the board. This is if we have two passes, one goes up to the thermal interface material and one goes down, then there's no use for this characterization parameter. So don't use that. It's a kind of a mathematical construct and not that we should use. Here you see a compact thermal model, boundary condition independence. We'll start to talk about boundary condition independent models. The JEDEC defines it. There's a JEDEC which defines a compact model is, I call it BCI, boundary condition independent model for an agreed set of boundary conditions, which means we have a range of validity. It can't be 1,000,000 degrees. It won't work at 1,000,000 degrees. We have a range of validity we set before that, and we do kind of an optimization process, somewhat like we do in reduced order modeling, for those of you who are CFD pointed. And we get a compact model, which you see here as 2D, but it's actually a 3D model. It has a network. It could be huge, and it's supposed to be not boundary condition dependent. So we use a big set of boundary conditions, and we change all the time the placements and the add resistors if we need. It's a very, very, very long process, but we don't have the detailed model, or perhaps we do have the detailed model, but we don't want to, as vendors, give the detailed model to the buyer. Why would we? This is our chip. This is our proprietary data. So we derive something which is equivalent thermally, okay, like the detailed model, but is not the detailed model. I mean, it only has thermal resistances, nodes. Okay, between two nodes there is a thermal resistance. You can see here one I did in IcePack. This is a detailed model. One of them is a detailed model. This is called Delphi. The Delphi models are what you should ask from the vendor. Every vendor, Stratix or Vertex or Microsoft, or would have a Delphi model. A Delphi model is a non-boundary condition dependent model. You see one I made here. I had a package. This is an actual experiment. Okay, this is an actual experiment and an actual simulation. Okay, so you do a simulation and you do an experiment and you play a lot with these. This one is 3D. This one can be I don't know, some point at a corner. It could be in the middle. It could be anywhere. It's very, very exhaustive and cumbersome thing to do on your own. But software like IcePack and FluteTherm can derive this, and I say it's an optimization process. They have a macro which can derive you a Delphi model from a detailed model if you have the detailed model. Okay? Any questions about Delphi models?
Hey, I have a question.
This is yeah.
The BCI models, it's something that I choose in the simulation program. It's because when I do simulation, I choose boundary conditions. So
no. You choose boundary conditions. The boundary conditions are what they are. But you don't want an internal, everything you see here is internal to the chip. It's a material. It's kind of the package. It's some kind of plastic, and inside there's a silicon, and there are little wires and many materials. They are not supposed to be affected. It's a closed. It's like a black box for you. they should not be dependent on which boundary conditions you use. Okay?
Okay.
So yeah, you set up the boundary conditions, but if you have a Delphi model, then you can use it like the numbers don't change. Okay?
Okay.
We can see how you can use a Delphi model in a reduced order model later. Did I answer your question?
I'm just curious about how this relates to the simulation itself.
This relates by that you have this FPGA on your 3U PCB, and then you have two choices. This 3U PCB is small; it's about 70 centimeters, 7 centimeters wide. 3.5 of them, 4 of them are real estate of the FPGA. And now you need to do a thermal analysis, and the most dissipative component is the FPGA. It dissipates 25 watts. What point is to use two resistors network, which means that, of course, you'll get a gradient on top of the chip, but it's not true. It's supposed to be isothermic. What point is to do such a simulation? I mean, what kind of knowledge do you get about the thermal environment of the chip? What can you deliver later to the reliability? I mean, so what you do is you ask Stratix for a Delphi model. Okay, you ask, I have the Stratix 5. And I want a Delphi model for iSpec or for flow term, and they would supply you with the model. I mean, all the time. They can give you these numbers, the theta JC and theta JB, but they will supply you with a Delphi model. Then you could get very accurate results, almost as if you use the detailed model. You could get gradients on the chip itself, where you can get, if the chip has 4 areas which dissipate heat, let's say this chip has 4 areas, one here, one here, one here, and one here, then it makes a big difference of how the temperature state is than if the silicon is a tiny piece in the middle. Okay, so there's a big advantage for a Delphi model. And again, I'm saying that using a boundary condition dependent value, besides the fact that it's only a 2 resistor model, necessitates that you use the same boundary condition they used in the JEDEC. This is just the 15.1 for Delphi. It necessitates that you open the JEDEC and see what boundary conditions there are. So if you have a client which wants or a system engineer who wants a thermal analysis, and he wants it at 55 ambient, you cannot do that. Then you cannot tell him, no, I'm doing it at 15 degrees, because that's when it's valid. Okay?
Okay, thank you.
Okay, I think I answered the question, didn't I?
Yes. Oh. You answered me.
If you
no, I just
ask again.
My daughter is screaming, so it's okay. Thank you.
Oh, yeah. Now we're going to look at the concept which became really hot. Most of you know them, reduced order modeling. A little bit about reduced order modeling. Reduced order
Hello,
modeling
Tom.
is good for yes.
I have one question.
Yeah.
Okay.
Shoot.
Yeah. Regarding that Delphi model, most of the
Yeah.
times we won't get the Delphi model from the supplier side. So that in that case, we used to use that 1D element, just theta JC and theta JB. So what could be the percentage variation accuracy between these two in Delphi and compact model was that? So is there from your experience? Can you explain that?
Yeah. Yeah. So for we have tons of chips on PCB. Most of them are passive, capacitors. It's important to know what the temperature is in the capacitor because it's important for reliability reasons, but it's a passive component. It means it doesn't dissipate heat. Most of our components are not that influenced by, they have a silicon, they're really simple, and they're not that important that using the two resistor model would be so harmful. Okay, when you're talking about component, which is the heart of the system, the heart of the SRU, okay, the heart of the PCB.
Okay.
You cannot make mistakes. I mean, you should have the best model you can get for the FPGA because this is the heart of the PCB. So a little component, a little power here and there, and a little transformer here and there. You can use the Theta JB. Most of them are built such that they won't suffer too much. But the high dissipated components are even designed internally in such a way that to dissipate the heat. I mean, the FPGA you saw before, the Stratix 5, is a flip chip. It means it has a theta JC, a theta J junction to the top, very small, like 0.1 watt per meter Kelvin. They are designed to be used with a heatsink. So getting the right temperature state on it could be very important. So do ask for Delphi models for such components. The ASIC. There's no reason why someone who has his own component, an ASIC, can't give you a Delphi model unless he's lazy. The big companies for FPGA have Delphi models for all the models. So does Microsoft. Okay, so just you need to contact them or find a web page in which you can download either iSpec or Floatant model. Okay.
Yeah. Thank you, Tom. Thank
And
you.
if you have FlowEFD, there is a module that can turn the Delphi model into a detailed model. That's really like an impossible thing because you can build an infinity of detailed models. But one which is equivalent, one which would be the Delphi model. So FlowEFD does that also today. FlowEFD, if you don't know, is the general purpose. It's like a SolidWorks flow simulation. It became quite strong. So those of you who don't want to do the simulation on Fluent or start CCM, use the 100 kilo hammer and use the general purpose software with which is pretty validated. Then Flow EFD with the electronics module can do a lot of it. Okay, did I answer your question?
Yeah, thanks,
And
Tom.
added a lot of
I got it.
yeah,
So,
and added a lot of stuff.
Yeah, thank you very much.
So the concept of reduced order modeling. This is actually a very important topic. It became very hot today. Reduced order modeling is like the major issue near machine learning, which the both of them are catching the eyes and the vendors of like ANSYS and Siemens and Star CCM are working hard to make a lot relevant. I can show you here. Maybe I have here a picture of a ROM in. Maybe I do, and maybe I don't. So maybe I don't. Picture of the configuration of the ROM. They made it very easy to use. So what is the reduced order model? It's taking the 3D finite element model if you do pure conduction, or finite volume if you do CFD, and turning it to under exactly like we talked about in the Delphi, under a few rules which are kind of an optimization process, a range of validity, okay, some kind of range, let's say between 5 degrees and 50 degrees. It takes a lot of points, in powers of 2, and it runs simulation over these points. After it does that, it doesn't do the simulation anymore. You can open viewer, reduce order model viewer, which is free, and you play with the boundary conditions, okay? You change the boundary conditions according to the range of validity that the ROM was made for, and you can see how the results change in each and every component. And it's a linear process because there are only so here I'm going to show you why we use reduced order models. Two main reasons. Why is it so hard? One is that I can offer the client, I don't want you to come back to me for every simulation that you have. You change a little bit around the condition, again simulation, again pay money. Let's prepare a ROM for you. You can download the free software. You can play with the boundary condition. If you want me to enlarge the range of validity of the model to be carried out for more boundary conditions, then you can turn to me. I'll do that and give you back the new ROM. Imagine that you have, okay, now we'll see that we can be reduced order. The second reason why we have, why reduced order model is a big thing, and it's the most important reason, is the appearance of the twin digital. Those of you who heard about twin digital, imagine the Fukushima with simulation by its side, which exactly the Fukushima nuclear plant, but it's a simulation. It controls the Fukushima nuclear plant. It can change the valves. It can lower the temperature here. Can a little bit lower the turbines here. Find a little bit eccentrics in the turbine somewhere else. It does everything, but it couldn't do it with CFD. Of course, it couldn't be on real time with CFD. So what we do is we produce a reduced order model, which gets in real time the boundary conditions from the actual Fukushima nuclear plant and solve them in real time because it's a linear solver. It's just arithmetics. And it could be really fast now if you use GPUs and CUDAs because they work really fast for arithmetic calculation. And then you have a Fukushima plan, and then you have a Fukushima reduced order model, which controls totally the plan, which could have prevented the disaster. So now we're going to see a network model of a system of components and with a combination of thermal resistive links. You know them, like the RJC, RJB, the ones from Delphi. We're going to see flow links, which is very interesting. We're going to have a reduced order model like the thermal resistance we had, but for flow. So it will be pressure and flow rate. And we're going to have capacitive nodes. If we want to do a transient simulation, then we can have capacitive nodes. We're going to link all of them in a representative network model. And it will faithfully replicate the model for a set of boundary conditions. So imagine yourself, we have a module. You see here the module, it has two fans. The fans can get a range of validity, a range of boundary conditions for them. We have an exhaust grill here. We do a CFD for a set of boundary conditions, okay? Kind of an optimization process. And we get a Delphi model, okay? We kind of set active components, what are do a CFD, a complete CFD, okay? And we see the rate of change where we have anomalies, where the flow might turn. I mean, of course, on a corner of a cube, you're going to have a recirculative flow. So then we have to use a lot more, perhaps, flow links there, okay? And what we get is kind of a division of areas, a map, still a CFD, resistive links, one node for each power device, passive devices if we want to extract details for reliability, the memories, everything is here. But we also have flow links wherever we find it important. Maybe we don't even find important what happened in here, okay? Maybe we can represent it by this node here, okay? But these are flow nodes and links.
Tom, can I ask a question,
they,
please?
Represent pressure. Yeah.
About the reduced order modeling, I would like to know how it differs from, I don't know, standard modeling, and what are his advantages or disadvantages or limitations?
You're gonna say it in a second.
Okay.
In just a second.
Okay, thanks.
Okay, so we did a CFD, we did our optimization, we took a set of boundary conditions, many boundary conditions. This is just one model. This model is going to go inside set a cluster of modules. Each module is going to have a ROM like this, and it's going to have its own boundary conditions. They're going to be perhaps even matched by some way, of course, because it's and we are going to have a ROM for each of these modules. Okay, So what we have here is combined fans, which get boundary condition, an exhaust, which is a grill, which is a kind of boundary condition, kind of pressure jump. A black box, which contains the network model that we extracted by using this procedure of optimizations of many boundary conditions, okay? And this big thing here is represented by nothing, boundary condition, and a black box, which is a kind of Delphi model. But look here, PCB nodes are the one you know. These are these thermal resistances measured in Kelvin to watts. But we have also fluid links. Fluid links would measure our pressure, let's say, through the